So I recognize a lot of familiar faces in here, but for those of you who don't know me, my name is Eric Woodman, and I'm from KTH, Royal Institute of Technology. The title of my talk today, like Chris said, is Evaluating Arterial and Plaque Elasticity with Shear Wave Elastography in an Ex Vivo Porcine model. And this is a collaboration between KTH, the Karolinska Institute, which is our medical university in Stockholm, and the Mayo Clinic College of Medicine in Rochester, Minnesota. So let's talk about what we're trying to accomplish here. Now, as we age, plaque can form in our arteries, depending on our lifestyle choices, such as our diet, our exercise habits, alcohol consumption, but also genetic factors. Now, if we oversimplify the problem, we can classify plaques into two groups. Soft plaques, also known as vulnerable plaques, which often have a soft necrotic core, and they're more likely to rupture, causing stroke. And on the other end of the spectrum, we have hard plaques, which are calcified plaques. And today, clinically, vulnerable plaques are diagnosed based on visual assessment of B-mode imaging, where physicians estimate the degree of stenosis in the lumen. And several studies have shown that this is not a good way to estimate vulnerable plaque. So we are trying to develop quantitative tools for the physicians to estimate mechanical properties of plaques and to better assess the vulnerability of them. And we're trying to use shear wave elastography to do this. And there's been a lot of work done previously to estimate arterial stiffness, and this work includes work by Bernal, who has estimated the stiffness in tubes and the carotid arteries of pigs. And also Matthew Quad, who has estimated the stiffness in vivo in a human in a pilot study. But we are primarily looking at plaques, and earlier this year we published an article where we looked at simulated plaques, phantom plaques, soft and hard ones, and we estimated the stiffness of them using our technique, and we compared it to mechanical testing and found very good agreement. And that's the technique that I'm presenting here today, and we're moving towards an in vivo implementation. But along the way, we're doing this ex vivo study to really optimize our technique before we go in vivo. So we are doing a porcine study in an ex vivo setting, and we're trying to do this with realistic in vivo pressures. And we want to try to optimize the acoustic radiation force push length to try to maximize the bandwidth of a propagating shear wave. And I'll talk about why this is important in a second. So I'm sure most everyone in this room knows what shear wave elastography is. We use acoustic radiation force ultrasound focused in the tissue, which generates a orthogonal propagating shear wave. And if we know the speed of the shear wave and we know the density of the material, we can estimate the shear modulus, under the assumption that the material is elastic, homogeneous, isotropic, and I should say linear on the end there. But however, a plaque, it's none of these things. So what we do instead is we look at the phase velocity of the propagating shear wave, and we use a model of a wave propagating through a thin plate that we fit to our phase velocity. So this is the equation that we use, and in there you'll find the shear modulus right there. So we vary the shear modulus until we get the best possible fit, which gives us a good estimate for the shear modulus. So in this study we had 5 porcine aortas, and we were trying to mimic the human carotid artery with these aortas, and the pigs we used were Swedish Yorkshire pigs. They were very small. And the dimensions of the vessel were approximately the same as the human carotid artery. So we wanted to create a simulated plaque. So what we did was we marked the midpoint of the artery, and we placed this pole through it, and then we soaked half the artery in formalin for 20 minutes to create a simulated calcified plaque. After that, we glued the arterioles in the artery shut and checked it for leaks to make sure it was watertight. And thereafter, we attached it to this fixture with a pressure sensor on it. We placed the entire fixture in a bath of saline and connected it to a water column so we could vary the inner lumen pressure in the vessel. We fixed the probe 1 centimeter above our above our artery. And so here you see the midline, and we have the plaque to the left here, the simulated plaque, and the normal artery to the right. So we use high-speed V-mode imaging to image our vessel, and we use a 2D correlation algorithm to track our shear wave. And from that, we can get our axial displacement maps with distance on the y-axis and time on the x-axis. And if we take the 2D FFT of that, we can go to the k-space, where we're looking at the wave number and frequency. We then do the simple equation, speed of the wave is equal to the wavelength times the frequency, and get the phase velocity map right here. And we crop out the data once we get the first discontinuity in our curve. So in this instance, it'd be right here around 1700 hertz. And we curve fit our model of the wave propagating through the thin plate to our phase velocity curve. We do a secondary curve fit by measuring the full bandwidth of our phase velocity curve and dividing it by 2, and we call this the upper bandwidth curve fit. And we have shown that we get a much better shear modulus estimate compared to mechanical testing when we do so. Okay, I'll go back for a second. So if you look at this graph, you can see that so we're curve fitting to the higher frequencies in our propagating shear wave. And we want to try to maximize the bandwidth so we can get as many data points as possible when we do our curve fit to give us a better shear modulus estimate. So that's why we're looking at the acoustic radiation force push length and trying to maximize the bandwidth. And we did this on one artery, and we varied the push length from 100 to 700 microseconds, and we measured the maximum bandwidth of the propagating shear wave. Thereafter, we measured the shear modulus, and we did this for 2 pressures, 60 and 120 millimeters mercury. And we did 3 measurements at each push length and averaged them and took the standard deviation. So let's look at the results. So these are 2 graphs for the 2 pressures. This is 60 millimeters mercury to the left, 120 millimeters mercury to the right. In both graphs, we're looking at the bandwidth on the y-axis and the push length on the x-axis. The blue lines are the wall, and the red lines are the simulated plaque. And what we notice is, as the push length increases, that the bandwidth of the propagating shear wave decreases, and that the bandwidth in the plaque decreases at a greater rate than that of the wall. So if we take the shear modulus estimates for all these measurements and plot them, so we're looking at the shear modulus versus the push length down here for 60 millimeters mercury and 120 millimeters mercury, you notice that that we can obtain consistent shear modulus estimates for push lengths of about 300 to 400 microseconds at both pressures. And if we interpolate these results to the upper graph, back to the bandwidth, we can see that we need a bandwidth of approximately 1500 hertz to obtain consistent shear modulus estimates, which is a very important result. And we also notice that we get the most the greatest bandwidth with the shortest push length, which is expected. So we decided to use the shortest push length, 100 microseconds, for our next experiment, where we looked at the pressure versus the shear modulus estimate for all 5 arteries. And yeah, we used 100 microseconds, and we varied the pressure in the artery from 20 to 120 millimeters mercury. And we estimated the shear modulus in the wall and simulated plaque. So let's look at our experimental setup again. So here we got the normal arterial wall to the left. We got the simulated plaque to the right. The left shear waves traveling through the wall. The right shear waves traveling through the simulated calcified plaque. And let's look at some sample results before we look at all the arteries. So we have the wall in the left column, and we have the plaque in the right column. And if we compare the displacement maps, we notice that the shear wave traveling through the plaque is traveling at a greater speed to that of the wall. And this is verified by fitting the model to our phase velocity data, where we see that the speed is greater in the plaque compared to the wall. So let's look at all arteries. So this chart is for the plaque, where we have the shear modulus on the y-axis and pressure on the x-axis. We've labeled the 5 arteries A1 through A5. And we can see that as the pressure increases, we also get an increase in the shear modulus estimate, which is expected. And that's true for the wall as well. However, notice that for the wall, the shear modulus is much less than that of the simulated plaque. Now, it's interesting to look at the in vivo pressures, so from 60 to 120 millimeters mercury. And for a lot of these curves, you'll see that we get a nearly linear response. So in the red and blue curve here, for instance, and the blue curve above it as well. And this isn't something that you'll see in vivo, but we believe this is a byproduct of the experimental setup. Remember, this is a static measurement, so we set the pressure, we perform our measurement, then we increase the pressure to the next step and measure again. However, in vivo, the pressure changes very rapidly throughout the cardiac cycle, and you'll see a nonlinear response in the shear modulus as well. So to conclude, we showed that we could estimate the shear modulus in 5 arteries with simulated calcified plaque using SWE with realistic in vivo pressures with diastolic and systolic pressures. And we showed that a minimum bandwidth of approximately 1500 hertz is necessary for consistent shear modulus estimates using phase velocity analysis. We showed that 100 microseconds results in the largest bandwidth for the propagating shear wave, and these are steps towards an in vivo implementation, which is where we're headed. There are many more results that I don't have time to present here today, but we are in the process of publishing this. The article is going to be called Shear Wave Elastography Quantifies Stiffness in Ex Vivo Porcine Artery with Simulated Plaque, and we've submitted this to IEEE TMI, and it's currently under review. So with that, I'll thank you very much for listening, and I'll take some questions.